Awesome. Okay, everybody, welcome to my talk this year. Waiter, there's a compiler in my shellcode. I think this is my 4th time speaking at NolaCon, so I missed a couple years. Our house flooded and everything was crazy. Life went on hold. But I'm back, and this is a project I've been working on for a few years. This is actually not connected to what I do for work at all. So something that I'm particularly passionate about, looking forward to sharing it. I'm Josh Stone. This year, I've been programming for 30 years. I started when I was 8 with a 286. And been working professionally in InfoSec for 19 years. I also have a real life, so I'm married, I have kids, had cancer 14 years ago. If you're interested in talking about personal stuff, let me know. A few years ago, I realized that being a nerd is unhealthy, and so to stay alive, I started Brazilian Jiu-Jitsu, and I'm a blue belt now. And if you can't tell yet by looking at the slides, I love the color graphics array. Currently, I work at FusionX on the research and development team there, part of Accenture. However, like I said, this project is about Evil VM. It's something that predates my coming to Accenture, and any similarity between my opinions and my employer's opinions is coincidental. Today I'm talking about a sort of core discontinuity in the way we deploy malicious code. So as an offensive hacker, as a pen tester, working with red teamers and so forth, we find ourselves in the position of writing malicious code. But most programming languages and most development environments are not designed with this use case in mind. So it's maybe tautological, but programming languages, as you may know, enable you to write programs so you can run them on your computer. Maybe you don't run them on your computer, maybe you give them to somebody else and they run it on their computer. But nevertheless, there's something really wrong with this as far as the core use case when you're writing malware. And that is that a hacker is not writing software to run on his own computer. He's writing something to run on someone else's computer. And that has a number of profound implications on how you design your programming language and how you develop your code. I'd love to go into more detail on this stuff, but I don't have a lot of time for the talk, and I'll kind of gloss over this just a bit. It's just important to note that a lot of programming languages make certain assumptions about how code is going to be written and how it will be deployed. With most programming environments, if you're thinking about C or C# or C++ or Python, Ruby, Lisp, whatever, you usually have the assumption that you're going to use the computer's resources, you're going to write files to the disk, the user can install dependencies, and they're allowed to run it. And none of these are true when you're writing malware. So when we try to use a lot of the common or very popular programming languages to write hacking tools, we're coming up against some design decisions that are working against us. We make it work, we get it done, but it's not necessarily easy. So I set out a few years ago after writing post-exploitation tools in all of those languages, C and Python and Ruby, C#, PowerShell, and anything you can think of, and some weird ones like Haskell that most people have never heard of unless you're a real programming language nerd. And I found that I'm always running into issues. What would an ideal malicious programming language look like? So first of all, a good malicious programming environment would make small programs. And this has become more of an issue in the recent developments because we've got things like Golang, which is very popular but produces a 3 megabyte hello world. And this is because they have highly abstracted languages that just pack a ton of stuff into the runtime environment. And even when they do pruning, you still end up with a gigantic thing. And you might not think this is too big of a deal, except that I've occasionally been in situations where, for example, I want to deliver my malware to a system through which I can only access it with a KVM. So what are my options? It's on an air-gapped network. I have a KVM. That means I have a keyboard. So I'm going to type my program in. I might hex encode it and type it in, or base64 encode it, type it in, and then upload a decoder and decode it so I can run my tool on that box. But you don't want to do that if it's 3 megabytes. Pro tip, if you're ever in that situation, you want it less than 100K. Because otherwise you're going to be there for a long time at 62.5 characters per second. Next, an ideal malicious programming environment would give me a lot of flexibility in how I execute my code. Most programming languages are designed to give you an executable, or maybe you have a program that is a text file that's going to be executed by an interpreter, something like that. There's usually a dead code version of your program, and that means it gets written to disk, and we hate that because that leaves IOCs. So ideally, I'd be able to package the programs that my environment creates in any different way that I want. And ideally, over here on the right, don't worry about trying to read it. It's just shellcode. All right, this is just a hex literal string in a C header. That would be my dream, is every program that comes out of this language is shellcode. Another interesting thing about malicious code is that I'm not just writing and using a program. I have to interact with it in a subversive way. I'm not sitting at the monitor. I don't have the keyboard. I can't use the GUI. I need to get information in and out. Now, a lot of programming languages don't really give you any sort of built-in remote I/O capabilities. Now, we do it because we implement our own. We write our own protocols and communicate with our tools. But it would be really nice if my malicious programming language did that for me. If I could write one payload and then use it with any different communication scheme that I need to and not have to change my program. Next, a good malicious programming language would give me a high ceiling and a low floor. So this is something programming language theorists talk about. A low floor means I can get as close to the metal as I can. I can get down to machine code and talk to the CPU. I can work directly with memory. I need things like pointers. But then if I want to be very productive, I want what's called a high ceiling. I want to be able to interact with my problem domain with high-level language abstractions. I don't want to have to get too busy with all of the details underneath, and I'd like to write my code quickly and run it. What I'm presenting today definitely has a very low floor, and I have the beginnings of the high ceiling. I haven't completely achieved all of my goals here, but we'll get there at some point. Another thing about an ideal malicious language would be that it would take into account the fact that the runtime use case for malicious code is very different from the runtime use case for regular code. Usually, if you go to create a software product, you'll produce it with some use case in mind. It accomplishes that use. You give it to the user, they run it, and it does the thing. When you're using a hacking tool, though, a lot of times you don't even know what you want your program to do until it's already running. Because you may get a beachhead on another system and collect information about that host, what user context it is, what it's connected to, what rights it has, and that will inform what choices you make about what you do next. So it would be nice if the programming language did this for me too, and made it very easy for me to dynamically load new behavior and change its functionality interactively over time. And now this is something we do actually accomplish with a lot of tools. If you look at a lot of the post-exploitation frameworks out there, they can dynamically load code. But a lot of times what they're doing is they're working against the machinery of the programming language. So for example, if you write your tool in C and you want to send new code down, you're going to write some more code in C, compile it, and build it into maybe reflective DLL. And that works, but it's also a pain in the butt. And it's not really the way you're supposed to do it. And what we're really doing is just making lemonade, if you will. So my first thought, after looking around at a bunch of things, was to achieve a lot of these goals, it would be nice if I could make my tool as like a little VM. It would be a shellcode that bootstraps a little VM that gives me some abstractions, system access that I need. And then I would connect to it remotely and have some sort of compiler or something on my side that would compile code modules to bytecode, send it down to the VM and run it. So imagine like a super tiny JVM that runs as a shellcode. But as I played around with a bunch of different prototypes and I tried different ideas, what I ended up finding is that I don't really need to do that. I can go so much further, and I decided that I've either gone completely insane or this is actually pretty cool. So after the talk, you tell me. So this is still a viable idea. I still have a few ideas on the VM side. But what I ended up deciding was that I was just going to put the entire language in the shellcode. So compiler and all, as you already know from the title, so it's not like I'm keeping a secret. And you see on the bottom here, I had already called the project Evil VM and blogged about it a bit. And I didn't want to take the VM off because who wants to Google for evil and hope you find a programming language? So anyway, it's a misnomer at birth. My apologies. So what I'm presenting today and publishing today too is Evil VM. It is a client-server model, so you run a server console on your own system and you deploy the agent. Agent runs on that host, connects back to you, and it is itself a compiler. In fact, it's a native code compiler, even with a little optimization. So if I pretend a little bit, I can even say it's an optimizing native code compiler. In this example, and you don't really have to read it so much, I'm just going to describe the shape of it. I send the source code for a function that, given a number, tells you if it's an even number or an odd number. And then within the system, I can inspect it, and this is all running on the other box. I can see the machine code that it generates, and I toss it over into Binary Ninja, and you can see the control flow graph. So to me, nothing says low floor quite like native code compiler. As far as communicating with it, there's another really interesting consequence of the design that I stumbled into, and that is that I/O becomes very simple. In a lot of remote execution frameworks, communication can be kind of challenging. You end up with this intermediate layer in your code. On the one hand, you've got your functionality. It's got a keylogger. It's got a RAM scraper. It runs commands, whatever. And then you've got some sort of transport layer, so you're communicating information across the network. And a lot of times there's this middle layer, which is all about defining some protocol for representing the data that goes back and forth. So you might wrap it up in JSON, you might wrap it up in XML, you might have some binary protocol that packs and unpacks messages. But a lot of times that actually introduces extra complexity. In this case, because the agent is itself a compiler for a programming language, the syntax of that language actually governs the structure of the data that goes back and forth. So my I/O layer is literally just a stream, bytes in and bytes out. You send a byte to it, that gets consumed by the compiler. Anytime your program prints data out, that's just bytes coming back to your box. So to add an additional I/O transport to this is very, very easy. You basically implement three functions. Start the I/O layer, send a byte, and read a byte. So you get those three, and then bam, everything works. And the way it's architected, it's designed so that you don't really have to change anything in your program when you change I/O layers, because the programming language is just a REPL with bytes in and bytes out. Evil VM is small. So right here's an example, a typical just TCP transport I/O layer. It comes out to 6,002 bytes. This is pretty nice. If you take I didn't check, I probably should have so that someone won't catch me getting the number wrong, but I think if you take MinGW and compile a basic hello world, so this is written in C, which is a compact language, you'll probably end up with an exe that is about that same size. So I'm able to pack a compiler for a programming language and swappable I/O layers and all this other stuff into something that's smaller than hello world, even written in C, compiled with most compilers. I'm not going to say you can't get it a little smaller, but you get the point. And it is a completely independent shellcode. The only requirement for the shellcode to run, to boot the compiler, is to have kernel 32. And if you don't have kernel 32, then it's not Windows, and it's not a supported system. This means you can package it any way you like. If you have a way to run code, then you can run the Evil VM agent. You could use a stager that you're already using. You could pack it into some existing framework. You could package it as executable, whatever you like. So I was really, really pleased with what came about as I got this thing working, especially once you bootstrap a language and you first start using it and you're like, wow, this is really powerful. I can't believe it actually works. You might wonder, so how do I get all of this stuff in there? It's a small shell code. I could make it smaller. Sometimes I bum something out and make it a little smaller, and then sometimes I think, oh no, I need to put this in for like better error messages. So I have to put something back in and make it bigger. But it's been hovering around 6 or 7K now for about a year. So how do I get this all in there? As we know, compilers are very big. If you've used GCC, you're sitting on top of a stack of almost 2.5 million lines of code. And in fact, in this chart, there are a couple things to realize, like Clang uses LLVM. So you might think, well, Clang is a small one at 800,000 lines, but it's actually sitting on top of 1.2 million lines of LLVM. It's a 2 million line compiler, just like GCC. And for reference, in case you're as old as me or older, Turbo Pascal down here at 14,000 lines of assembly is about the smallest compiler I could find without being just a trivially toy compiler. So that's pretty tiny, and that's roughly in the ballpark of Evil VM's compiler. But you see, we have to go back like 30 or 40 years before anybody cared how big these things were. So how do I get this in there? The main observation is that we can stand on the shoulders of giants and we can see farther. If we look back at the way computing was, it was a memory-constrained environment, very light on resources, and everyone had to think about how big their code was. These days, it doesn't matter because drives are gigantic and everybody has lots of memory. So programming language designers simply don't care about it. So I think there must be some law of nature that compilers will expand to fill the container available to them. So I found a lot of inspiration in reading old Dr. Dobbs journals and other things from the early 80s to see how people were putting programming languages together on computers that had less than 64K of RAM. And we had compilers, so it's definitely possible. What I ended up settling on is inspiration from Chuck Moore, who invented Forth in 1970. Has anybody ever written a Forth program? Yes! Awesome. So Forth is ideally suited. We'll get into some of the details about that. One of the reasons is because Chuck Moore was not a computer scientist, so he didn't know how you're supposed to write a compiler. And he found a better way, well, better. Maybe some people would get upset about that. He found a different way to do it, and in this case, it's ideal for my scenario. So let's look briefly at how compilers work. You could argue with any computer science professor about whether these are the right names for the right number of phases, but we're hand-waving a layman's compiler course right here. Compilers go through some number of phases, turning your source code into a program. And some of these are like a focal point for some of the hardest problems in computer science. So compilers are cool, and a lot of stuff goes into them. The first piece is lexing. Usually, you take your program source code, you have to break it up into pieces. So you can see like here, main with the parentheses next to it, those are two different pieces, right? One is an empty argument string, or argument specifier, descriptor, and then the other is the name of a function. So the lexer breaks that up. Some languages are easier to lex than others, but lexing isn't really that hard of a problem. You just have to do it. Up next is a much harder problem, that's parsing. So we have to take that list of lexemes that came out of the lexer, and we arrange our program into this hierarchical structure, the abstract syntax tree. So this lets us do a couple things. One, the compiler can tell by analyzing this what order things have to happen. If you look at this one, we have to add 3 and 4 before we can call printf, right? So, of course, a real compiler will realize those are constants and optimize it out, but that's beyond the scope of this talk. Once we have this arranged, we now go through several rounds of transformation. Most compilers do their optimization here. They may actually translate the program into different languages, intermediary representations. And some of what's going on here might be optimization. It also might be proving things like type safety, proving that the program is correct or conforms to the semantics of the language. This is probably the biggest and hardest problem in a compiler. And if you look at GCC, I bet like the vast majority of that 2 million lines of code is probably devoted to this. Once you know how the code needs to be organized and what order it needs to be executed, etc., we go into code generation, or you turn this into assembly or machine code. And this can possibly be a hard problem because you might have to do a lot of register allocation. There's some neat algorithms in there for making good machine code, better than humans can make anyway, mostly. And then finally, once you have a bunch of machine code, you go to linking. So your program uses a library. It needs to know where that's going to be in memory and be able to call it. Everything needs to find out where everything else is in order for it to run. So Forth works in a fundamentally different way. Like I said, Chuck Moore was a physicist, I believe, and not a computer scientist originally. So he had never read a book on compilers and didn't know that this is what you're supposed to do. So in Forth, lexing is blindingly simple. It's identical to splitting a string on white space. Any two things that are separate from each other have to have white space in between. So lexing's easy. Parsing doesn't exist in Forth, usually. And the reason is because Forth is designed so that you can compile it in one pass. You read in a word, you compile it. You read the next one, you compile it. You don't have to arrange it and figure out the order of operations. This comes from things like reverse Polish notation and the stack structure of the language. Since there's no parse tree, there's no transformation, so that goes away. Code generation boils down to two things. You have to be able to compile a function call, which means you find where the function is and then write like an E8 and then the distance to the function. And then the other thing is to put constants on the stack. So the code that says, if my program needs to put 3 and 4 on the stack and add them, there needs to be some code that puts 3 on the stack and some code that puts 4 on the stack. So those are really, really easy, much simpler than all the register allocation and assigning to places in memory and everything that other compilers have to do. And then Forth is usually a live coding environment. There's usually not really a dead version of your program that needs to be run later. In fact, a lot of Forth compilers have no facility for creating an executable. You just can't do it. Every time you run your program, you compile it. It happens in one pass and it's really fast, so you never notice. But that means that linking doesn't really exist. So you can see Forth compilers can obviously be made much simpler and much smaller than other languages, but it is a fully functional language. It looks a little bit like this. So over on the left, we have the way you do a math expression in a typical language. And this has to be parsed, because you have to figure out what order this goes in. There are parentheses, there's order of operations. This cannot be necessarily compiled in a single pass, or if it can, it's hard. In Forth, it works differently. You put the arguments to a function on the stack, and then you call the function. It pulls the data off the stack, does something to it, and puts it back. You might think that sounds low level and archaic, but it's exactly the same way that the JVM works. It's the same way the CLR works. There are a lot of stack-based VMs that you probably use and don't realize it. Same thing for syntax like conditionals. Instead of having this structured syntax on the left, on the right, we put the two things we're going to test. We have some operation on them. We're doing a bitwise AND here. And then if just takes the thing on top of the stack. If it's true, it does one thing. If it's false, it does another thing. And then function calls work the same way. You put the arguments on the stack first and call it. I would absolutely love to get into the formal type theory of concatenative languages. I just don't have the time. About half the slides in this PowerPoint deck, LibreOffice deck, are hidden slides because I just can't get to everything. The other thing you need to know about Forth is that everything is built around the dictionary. This is a central data structure. It's kind of like a Python dictionary, if you're familiar with that. This is a data structure that maps names to addresses in memory. So imagine every function you define has to exist in the dictionary, and then every variable that you use is probably in there too, and some other stuff that we can hand wave around for now. All right, so the next slide, don't try to read it too hard. What I want to point out here is that this is pseudo Python for the compiler. This is actually the whole compiler. The hardest thing in the compiler is converting strings to numbers. That actually takes longer than any one of these phases in here. So the compiler really does a very simple thing. It reads a word and it compiles it. There are a couple cases for how it compiles it, like I said before, and that's it. So the compiler for a simple Forth boils down to about 1 to 2 pages of assembly. So that's how I fit it in a shellcode. So when the evil VM agent starts up, the shellcode itself has a very small dictionary. This is everything you can do in the language. Remember, you can't do something unless you send that word to the compiler, right? So I can't run code without submitting code, and these are all the things that can be code except for numbers. Obviously, I'm not going to list all the numbers. If you look through here, you'll see things like, there's some math. There's some words in here for manipulating the dictionary, creating entries in it. It's not too important that you understand by looking at them what each of these do. This is the minimum that's required for the compiler to work. When the shellcode runs, it is a fully functioning compiler. However, it doesn't have some things. Like you'll notice that the only control flow in the core dictionary here is tail recursion. And there are no conditionals. There are no ifs. There are no loops. And you might think, well, what good is a compiler that can't do loops and can't do ifs? And it turns out that most of Forth is written in Forth. And once you have a technically barely functioning compiler, it can compile the rest of the language. So this is the source code for if. You can tell that these are special because they have this little IMM at the end. These are immediate words. So instead of compiling them, the compiler runs them. And that means when you define an immediate word, you are extending the compiler, and you can add syntax to the language. So it's a programmable compiler. And that's another reason it's beautiful. I don't have to put the whole language in the shellcode. You just have enough. This is an example. This is how loops work. If you're interested in what some of these primitives do and exactly how this works, get me afterwards. I don't mind talking about it. But I'm sitting at 27.5 minutes, and I wanted to make sure I had time for some demos, because as fun as compiler theory is, I think everybody will get some fun, especially if you're like, I like programming, but I'm not really a programming language nerd, but I like hacking, and I know what hacking looks like. So let's do some stuff that looks like hacking. And for that, I'm going to threaten the video recording here by switching to, which one is it? No, I'm on join displays. Mirror, there we go. All right, don't look ahead. So Evil VM exists. You can check it out at GitHub now. I'll have the link up later. But Evil VM is a number of different components. Is this readable? Should I make it bigger? How's that? All right. I want to make sure that this is consumable by everybody. So the shellcode is fairly customizable, and here's why: big font sizes. All right, just for a sec here. I'll make it bigger again in a sec. So when you mint a copy of the shellcode, you choose your transport layer. Currently there are these ones. I have half the code written for ICMP. If you have other ideas for cool ones, let me know. The one caveat is they have to be written in assembly. And you'd think HTTP is hard, but it turned out to be way easier than I thought it would be. You can configure some things with your transport layers, and then there are some options for encapsulating it. We'll just make a basic agent for now. So we'll choose the network transport with TCP session. You tell it where it goes. So here's the IP. Oh, I'm sorry. There you go. All right, so I tell it where I want it to connect and what port. We'll just generate raw shellcode, and I won't do any fun encapsulation or encoding for now. We'll write this out. All right, so here we go. There's my screenshot from before, 6,002 bytes. If we look at this guy, of course, here we go. So yeah, you can see some evidence that this looks kind of like shellcode. You can see our imports from kernel 32 and so forth in here. And this is runnable. Let's go ahead and start the server. All right. I should have another. There we go. Pay no attention to the man behind the curtain if you want to see what I'm doing. So I have a script. What this does is it creates a task with the task scheduler that runs a PowerShell snippet that downloads the shellcode over HTTP and runs it. So this is essentially fileless-ish, maybe. All right, and hopefully this will work. If it doesn't, I'll go click on it because I don't want to take too much time. Here we go. So we get a session in. So each session, and in fact, let me go ahead and I'll run one manually just for kicks here so you can see. Uh-oh, here we go. Don't look, that's for later. We'll run. So here we got 2 channels. I can interact with these channels so we can listen. We see we got 2 channels. Each channel gets assigned a Crayola crayon color because this is my own project and I can do whatever I want. It's basically a hashed value based on the username and the machine GUID. So one of these, if we, right now we're talking with session 1, I can run just a regular command with the bang bang word here. So let's do who am I? So I'm running as system here. And if I switch, this guy is running as someone much less interesting, just a regular user. So this is a server, this is the agent working. There is a basic network payload that includes a bunch of useful functions, right? So we can look at the file systems, and this is all done without process execution. I'm just using Win32 API calls to do all of these things. And then the server can send new code down to the system. So the compiler is just sitting there. It's got its body of defined words. What is it, Cliff? Yeah, now it's a little bigger now. So right now I'm using 79,000 bytes in the dictionary because I've consumed and compiled some code. Yep. Yeah, as soon as it connects to the server shoves down the rest of the core API. It's optional. You can use it just fine, but I was just kind of waiting for that step. Yeah, ifs are nice. They come in handy. And then we can send more code if we want. So say I'm in an environment where I want to get some net stats, but I don't want to run netstat because I know that they're running some EDR that says, nobody should run netstat, and it's going to get bubbled up to instant responders or something. So I'd rather not go out of my process. I'll just use some Win32 API stuff. So I have a module. I'll load that, netstats.fth. Most of the modules, I have a little bit of help here, so it tells you what it defined. If we look, we can see that the words that exist in the system now include routes and netstat and stuff like that. So we can run a netstat. I thought this was clever. It even tells you which one is its own. So this will give you an idea. Working with it, it works kind of like a shell. And you can add whatever functionality you need to it, whatever's handy, just by adding words that do what you need. At any time, your program can take control of the input stream and then do stuff with it. So it turns out to be a very, very exploratory style of programming. It feels a little bit more like a shell, except that if I take one of these words like netstat, I can see it. And here's the machine code for netstat. Now this calls to some other functions. It takes more than that much machine code to do a netstat. But you can always see what's going on underneath. All right. Now let's see what I'm supposed to do next. Uh-oh. All the way at the beginning. Uh-oh, those are hidden ones you're not supposed to see. All right. Yes, keylogger. Actually, let's go ahead and... Oops. All right. So I want to show you a little bit about what the code looks like. I showed you snippets before that were probably not particularly interesting. Good, I'm doing fine for time. So a keylogger might look something like this. This is a functional keylogger. It's a pedagogical example, so there's some extra things you'd want it to do. But this is just an example of what fourth code looks like and how I'm using it to do something malicious. So usually you read fourth programs from the bottom up because you can't call something that isn't already defined. So we start at the end and we see that to keylog means we go into a loop. This key question until, that just means we exit the loop if the user ever sends input. So I can get out of it if I want to interact with the compiler again. So in this loop, we test the keys, and then we wait 8 milliseconds, and we just do that forever. So you might say, how do we test the keys? That's up here. So there are possibly 256 scan codes that we might reasonably check. It's actually, if you keep it under, I think, about 220, you'll get most of the keys on a normal keyboard, but it's pedagogical, so we do them all. So this is like a for loop. I give it the bounds. I'm going to go from 0 to 255. And then between do and loop, that's what happens in the loop. I is always the loop counter. And so what I'm doing is I put I on the stack. So we're going to test key 0. We're going to test key 1, test key 2. And then I'm going to call the test key function, which looks something like this. So test key, what we do is we check, is it down? So the is down is a function that calls a Win32 API call that says, is this key pressed right now? So if it is pressed, then there's some stuff we want to do. So that calls the function do down. If it was not pressed, we just want to make sure that in our little data structure where we keep track of all the keys, that we've marked it as not pressed. So we unset that key in our key state. Make sense? Do down, we check if it was down already. Right? If it was down, then a keystroke has not happened. So we do nothing. We just drop it off the stack and we're done. But if it wasn't down before and it is down now, then we've detected a keystroke. So we set the key state and then we report the keystroke. There's more to it than that. I don't want to belabor it too much, but I just want you to see a sample of code. I can show you, oops, if I can remember Emacs. All right, so maybe I can make it just a bit, almost. All right, so this is the whole thing. From soup to nuts, this is the whole keylogger that I'm showing today. At the top, you can see I'm importing user32.dll, and I'm using the foreign function interface, which comes with the basic payload, to import these functions. And they get wrapped up with fourth functions. You can call them just like anything else. They take their arguments off the stack like any fourth function. So you read it from the bottom up. This is the same code. I just didn't space it out the same way. This is more of a traditional way to structure fourth code. But this is the whole thing. So let's go ahead and run that and see if we can log us some keys. So we'll load the keylog2.fth. So it's loaded. If we check our dictionary, we have keylog, which is the magic function. So we'll start keylogging. And this is on Jazzberry Jam very intentionally because system is running in not the same desktop as the user. So I want to make sure I get some keystrokes for my demo. So let's grab something here. This is for the next demo. So here you can, keystrokes are coming in. Hello, NolaCon, right? SSH, router, root, password 123, right? Because that's how everybody logs into their router anyway. So you see keylog's coming in. Remember, we exit the loop by submitting something, so I just press enter a couple times and we hop out of that. So what I've found is I theorized that this would be a nice way to develop malicious tooling, but it turns out in practice it's actually really fun. You can write this interactively. I can write a function. In fact, I've even found when I'm exploring the Win32 API and I've never called a function before, why would I write a harness in C that does all of this stuff when I can just import it, wrap it, and call the blasted thing? So this turns out to be a very, very quick cyclical development process. Now, the next thing I want to show is the low floor. I said, native code compile, we want to get down to the machine. I have an example, a situation I ran into in real life. I was trying to understand the way some other tool, a security tool, how it worked. And it was doing something with threads, thread local storage. And we're looking at that, and I thought, I want to know what some of the fields are in this particular data structure. If you're not familiar with Windows internals, there's this thing called the TIB. So this is the thread information block. It has a bunch of useful stuff. Windows puts things all over the place in memory, and there are some things that your program has to be able to find. So a lot of that stuff goes here. And in modern Windows, in 64-bit Windows, it's indexed off the GS register. And most programming languages don't give you a way to index something off the GS register. There are actually some C function calls to do this, but it's a pedagogical example. We'll go with that. So the first thing I need to do is I want a function that lets me pull data out of memory indexed off that GS segment register. So I know what that looks like in assembly. It looks something like this. GS RDI. Why am I looking over there? It's mirrored. So this is what I would want my function to do. So let's just put this in a function. So I'll take this machine code. You can do it with longer shellcode if you want to. So let's define a new function. We'll call it @GSX. Is fourth nomenclature for read something from memory, usually. And I want to index things one quad word at a time, one 8-byte register size value. So we're going to take an index. We're going to treat the GS segment register as if it's an array. So I'm going to take an index in that array. I'm going to multiply it to find the byte offset, if that makes sense, if you're keeping up with it. And then we're just going to have some inline machine code here. So right there. So now I've made this function. We can look at it. If you look real closely, quickly enough, you'll see that code that I just put in there. Somewhere. Should be 6.5. And we see it. There it is. Bam, right there. So let's do some inspection. Let's take a look at the TIB. I can use braces to do an anonymous function because I don't need to fill up the dictionary with useless stuff. .pre just means I'll make it look pretty. You'll see in a sec. Let's look at the first 12 quad words in that region in memory. We'll do a do loop. We'll print the index of it. We'll grab that value. We'll print it, make a new line, finish our loop, make it pretty, and then we'll execute this anonymous function. So now I've run this machine code from scratch in my function, wrapped it up, and you can see some interesting things in here. Now one of these, I forget which one it is now, I think it's 7032, might very well be my process ID. Let's see. Yeah, 7032. So for example, if you want a quick way to get your process ID, just grab it from there and don't call the Win32 API call that probably grabs it from there. But this, I hope, shows at least a little glimpse into the low floor. You can go as nerd as you want with this type of environment. And now I want to show the high ceiling. Do I have time, please? Yes, I have time. All right, so let's get back to Emacs. All right. Yes, I'm an unapologetic Emacs nerd. Emacs is life. All right. So I was just showing machine code. I'm going to show something that's much higher level. Wow, that's still pretty small, isn't it? Yeah. I hear you. All right. I know that joke. All right. So anybody seen context-free grammars before? If you've ever done compiler stuff, I'm sure you have seen them. Does this look vaguely like a context-free grammar? What I'm doing is I'm defining a matcher for a credit card number. So in this case, a credit card number is matched by a parser, and it's either an ASCII credit card number or it's a Unicode credit card number. Make sense? So the vertical bar is an OR in this parser framework. Now let's go up to the next one. We called CC number lang from there, so here's the other instance of it. So CC number lang is a parser, and it will match either a separated credit card number, right? So that's 4 digits with a separator, 4-digit separator, followed by something that signals the end of the number. So something that's not a number. Could be the end of the string, could be punctuation, just something not a number. Or if it's not that, it's 16 digits followed by the termination. And then this technically has a bug, but we'll hand wave over it because I want to show recursion. Or it's a sentinel value, which for credit card stripe data is a semicolon usually, followed by a digit, and then a credit card number. Make sense? And then if we go up a little farther, we'll see that a separated credit card number is 4 digits followed by a separator, and then 4 digits a separator, etc. And this will actually match the separators. So if you have a hyphen for your first separator and a space for your second separator, it'll say, no, that doesn't look like a credit card number. Because usually people keep them the same. As we work our way up this parser stack, we get to things like, a digit. We grab a byte from what we're inspecting and see if it's within this range. It's from 30 hex to 39 hex, etc. So this is high level. And what you may not realize just by looking at it is that these are done with those immediate words I was talking about. So parser, ampersand, and pipe, these are little compilers. And they extend the fourth compiler. So when you define one of these parsers, it compiles it to machine code. So this is actually a native code parser after it's done. So this isn't like a parser interpreter or something that just has some specification of a parser and it processes it. This actually uses a CPU to parse. I'll show an example of this running. Maybe. All right, let's see. So we had that notepad process, right? PID 4356. And I happen to know that at this particular network, they call their payment processing application that sends the card data to the gateway notepad. So we want to see if it has any credit card numbers in it. All right, so be prepared. So procdump, this is a module that brings in a lot of stuff. A lot of these are syntax extensions. So structures, I want to have structures because I need to use some Win32 structures in here, so you can define those. That's actually a bolt-on. Named locals, I have some functions where I don't want to just keep track of stuff on the stack, so there are named locals in here. And parsers and strings, and there's the LUN algorithm, so I can check the checksum and everything. If you're interested, you can pull the code out and look at how these work. But this gives me a sort of functional programming interface for scanning memory. What I do is, like right here, this example is pretty much what I'm going to run. Let's find that again. So process 4356, and then I'm going to quote a function. It's going to be the scan pans function, which uses that parser code I was just showing you. And then I'm going to have the each region function map the memory from that other process, pull it into my process, and then run scan pans on it. So you could use this like you could make another function that searches for substrings, or another one that looks for NTLM SSP, because that's pretty useful sometimes. And you can use the same line just with a different function in here. And in theory, when we run this, we should be regaled with a variety of seemingly correct pan data. And remember, this does the LUN check. It does, all the stuff you'd want to. And it tells us the address of memory in that other process where it is. So if I'm like, hey, that looks like the segment of interest, I don't want to dump the whole gig of memory that it's got. I just want this piece. So hopefully this shows you a little example of the high ceiling that is possible. It's not perfect. I'm still working on some ideas for making it a little bit easier to program at a higher level. But to be able to extend this, if you imagine writing this code with all of your ifs and loops and other things, it gets really hairy. It suddenly gets very pretty when you can just say, here's a grammar for credit card numbers. All right, where are we? Yeah. All right. So that's it for demos. I hope that went okay. You can get hold of EvilVM and you can run it. It's very, very alpha. I change it a lot. Everything in the core API is pretty static, but every once in a while I change things. Just a few weeks ago I thought, if I'm going to release this thing, it'd be nice when there's an error if it told you what function it was calling when it had an error. It's like I added that a few weeks ago. So yeah, stuff changes. But if you're bold of heart, willing to try something that probably has bugs that I've never found because I know what not to do, I go ahead and pull it down. I'm releasing it under MIT license so that nobody will fuss at me except maybe the really, really Libre people. And you can find there's a little documentation. I'm still fleshing that out, but there's a little intro, shows you how to set it up. and then walks you through a couple of use cases on the doc site, evilvm.ninja, and then you can get the code on GitHub. I think, I successfully unprivated the repo early this morning, so if it did work, awesome. Cool. And I'm more than happy to entertain either suggestions from people, or if anyone wants to play around with it, I'll be deeply honored. This has been a labor of love for a couple of years now, playing around with all kinds of ideas. And so if you're interested in using it, and especially if anyone's interested in contributing, I'll probably accept just about anything. So there are things I want to do. How are we for time? All right. The biggest thing I want to improve is resilience. So when you're running native code, you can crash your process, and I want to make it as crash-proof as possible. So my biggest idea is to copy an idea from Erlang. So you get your initial agent, and it becomes like a little hypervisor for running other instances of the agent beneath it, and it proxies communication to them. So if one of those goes haywire, well, you've always got the hypervisor. So I'm working on some ideas for sort of HA, self-healing kind of stuff. I also want to make it a little bit more user-friendly. I understand that as beautiful as Forth is conceptually, it's kind of an odd language. So I've been thinking about trying to come up with something that's sort of in the basic Lua Python continuum as far as another level of language that you can use to interact with it. It won't be too hard, I think. I've already got parsers. And I should be able to write this in Forth. And if you wanted to use that, you just send that module down, fill up your dictionary with a lot of new stuff. One of the most fascinating articles I've ever read in my life is in an issue of Forth Dimensions magazines, which is the trade journal for Forth back in the 80s. It's a guy who writes a Forth program that extends the syntax of Forth until it accepts the syntax and semantics of tiny Pascal. So you take a few things out of Pascal just to make the grammar a little easier, and then it begins to consume Pascal programs as an interpreter. It's just disturbingly beautiful things. More transport layers. I got a couple in mind. ICMP's almost there. I've got the scaffold. I just need to finish it. And then I want to put up some videos and stuff for demo, because in the Forth community, it's not the most active community in the world, and there need to be some more videos. So I'm going to do my part, and of course document stuff. You can find me online. I tweet about 5 times a year, and I try to make sure it's substantial. So it might be better than all the other people you're following. So feel free, grab me on Twitter, email me, feel free. And I was really proud of my slides. I don't know if you know this. In CGA, the magenta is not red and blue. It's actually red and blue and 1/3 green. And the cyan is the same way, just different color channels. So this is legit CGA. All right, anybody got questions? And if you want to talk about stuff that'd be longer than like a question in the last 5 minutes, grab me afterwards. I'll talk forever about this topic. You can, actually. So there's a function called forget. When it starts, it sets a point in the dictionary, and you can run forget, and it'll forget everything up to that point. And you can reset the forget point. I do this for incremental development all the time. I get something working, and I set the mark, and then I try something else which borks forever, and I always forget back to that spot. Yeah.
That sounds like there's no way for me to unload something. If I'm loading 3 modules, I can't unload the second one.
Right. Yeah, they're also potentially all interrelated. Absolute worst case, there's a function that puts the entry point on the stack, and there's a function that starts a thread at some location in memory, and you can always just start another one. Going, gone. All right, thank you.